Welcome to Engineering Systems. I'm absolutely thrilled to kick off this 11th explainer, which marks the beginning of a brand new series called Availability Patterns. Now, in our previous series on consistency patterns, we spent a ton of time exploring how distributed systems manage data correctness across multiple nodes, right? We got into strong consistency, eventual consistency, the whole shebang of making sure users see accurate info. But today, we're shifting gears to the second major pillar of distributed systems. And honestly, this is the topic that dictates whether your system actually survives contact with the real world. Here is our roadmap for today. We'll start with consistency versus availability, define what availability actually means, look at the real cost of downtime, confront the inevitability of failure, and wrap up by introducing availability patterns and single points of failure. Let's jump in. Section 1. Consistency versus availability, the pillars of distributed systems. Notice the core contrast here. Consistency is all about making sure users see the correct data. If a database is perfectly consistent, every replica is perfectly synchronized. But here is the catch, and it's a big one. The most perfectly consistent database in the world is, well, completely useless if your users can't actually reach it when they need it. Availability focuses entirely on making sure users can access the system. That brings us to Section 2, defining availability and measuring reachability. So, before we can design highly available systems, what exactly is availability? At its core, it's the ability of a system to successfully respond to user requests. It's basically binary for a single interaction. You send a request over the network and the system responds correctly, boom, the system is available. You get an error or a timeout, it's unavailable. Sounds incredibly simple, right? But measuring this across millions of requests over a massive timeline is where system design gets really fascinating. We usually measure this in percentages, or what we engineers like to call nines. And it's wild how a tiny decimal change alters your reality. Look at a target of 99%, just 2 nines. You can literally be down for days out of the year and still hit that target. But add just one more 9, 99.9%, and suddenly your permitted downtime shrinks to a few hours. Jump to 4 nines, 99.99%, and you're allowed mere minutes. 5 nines, 99.999%, we're talking just a few minutes of downtime for the entire year. You can see why fighting for that extra decimal point becomes an absolutely crucial engineering challenge. Let's move to Section 3 to see how this translates into the real world. We're going to look at the cost of downtime through a fictional case study using a platform we'll call FoodDash. Imagine FoodDash is a massive, highly realistic food delivery platform. It's 8 p.m., the evening dinner rush is hitting hard. Millions of hungry users are going through this exact journey, opening the app, browsing restaurants, adding food to their carts, and hitting place order. The system is handling absolutely massive peak traffic. And then, right at the height of the rush, a critical server fails. Suddenly, millions of screens flash this exact message, service unavailable. Now, you might think it's just a 10-minute outage, no big deal. Wrong. The fallout is immense. Frustrated customers instantly switch to a competitor's app. Restaurant kitchens just sit idle. Delivery partners are stranded on the street waiting for jobs. Business revenue absolutely tanks in real time. And most importantly, you've shattered customer trust. This shows exactly why availability isn't just an abstract technical metric on a dashboard. It is a critical business concern. A 10-minute outage at the wrong time costs millions. Which brings us to Section 4, the inevitability of failure. Let's talk about the harsh reality of engineering. I want to pose this question directly to you, the system designers and back engineers watching this. Can a system ever truly achieve 100% availability? Like, can we guarantee that the service unavailable screen will literally never happen? Well, in theory, it sounds wonderful. In practice, it's almost impossible. And the reason is simple. Distributed systems are built on top of physical reality. And physical reality breaks. Hardware fails. Hard drives crash. Network cables get cut. Power outages happen. Even massive cloud providers experience regional outages. Add in software bugs and, human deployment mistakes. Failures are not exceptions in distributed systems. Failures are expected. So, we have to make a huge mindset shift. Modern engineers do not ask, how do we prevent every failure? Because we know we can't. Instead, we ask, how do we keep the system working when failures occur? That single question is the foundation of availability engineering. And that mindset brings us perfectly to Section 5, Availability Patterns, Designing for Resilience. Availability patterns are basically our architectural toolkit.
They are design techniques that help systems remain operational and continue serving users despite the inevitable failure of their underlying parts. Think redundancy, where we run multiple servers instead of one. Think database replication, failover mechanisms, load balancing to distribute traffic, automatic recovery, and failure isolation so a bug in one tiny service doesn't crash the entire platform. We aren't going to deep dive into the nuts and bolts of these today, but these are the exact techniques we'll be unpacking in our upcoming explainers.
But before we can fix a system, we have to know how it breaks. Let's look at Section 6, Single Points of Failure, the ultimate enemy of uptime.
Let's look back at FoodDash. Imagine if they ran their entire global platform on just one massively powerful server. It handles everything beautifully right up until that specific server crashes. In that exact split second, the entire business goes offline. That server is a single point of failure, a component whose failure brings down the entire system. Identifying and removing these single points of failure is the absolute first step toward building high availability.
Because remember, the goal of modern system design is not to avoid failure entirely. That's a losing game. The goal is to avoid catastrophic failure. The goal is to make sure that when a server inevitably catches fire, the user ordering their dinner never even notices. Let's do a quick recap. We looked at consistency versus availability, defined availability as reachability, saw the devastating business cost of downtime, faced the reality that failures are inevitable, introduced availability patterns, and highlighted the danger of single points of failure. This explainer is really just the foundation for our entire availability patterns series. Next time, we're doing a deep dive into single points of failure. Because before we can build highly available architectures, we have to deeply understand what brings systems down in the first place. Please make sure to subscribe so you don't miss that deep dive. And thank you so much for watching Engineering Systems. I'll leave you with this final thought. If your system failed right this second, how many of your users would actually know? Think about it. See you next time.